Hello and welcome back. In this video we're going to work some problems from the back of Chapter 8 so that we can try and apply some of these concepts that we've been learning to some actual problems themselves. So these are the three problems we're going to do from the back of Chapter 8, 8.8, 8.18, and 8.36. So let's start with 8.8, and I'll just read it to begin with. A car moving at 10 meters per second crashes into a tree and stops in 0.26 seconds. Calculate the force that the seatbelt exerts on the passenger in the car to bring him to a halt. The mass of the passenger is 70 kilograms. So let's write down some of the information we're given here. We know that the initial velocity of the passenger is 10 meters per second. Obviously, he's traveling at the same speed as the car. The final velocity of the passenger, and remember, we're using primes for final quantities. The final velocity of the passenger is 0. He's brought to a halt. His mass is 70 kilograms. So this is the information we're given in the, and also that the time it takes to stop the passenger, to bring him from the 10 meters per second to a velocity of 0, that time is 0.26 seconds. We want to know what is the force being exerted by the seatbelt. So the force by the belt equals question mark. Notice that is the only force that's acting horizontally. Let's pretend that he's not getting any force from the steering wheel. In reality, we know that when people are in accidents, they will push against the steering wheel during the impact, and the steering wheel then will push against them to change their momentum. In this problem statement, we would have to know how much force was being exerted by the steering wheel on him to be able to quantify that part of it, but we're going to have to assume that it's 0. In other words, the only thing that's stopping him is the seat belt. Okay, so let's go ahead and use this information to find that force. So using Newton's second law, we know that the change in momentum that the passenger experiences is equal to the net force times the time that that net force is being exerted. And in this problem, the net force is equal to the force exerted by the seatbelt. That is the sum of all the forces horizontally acting on the passenger. Everything here is horizontal, right? We aren't dealing with anything vertically because the momentum isn't changing vertically. Vertically, his momentum is 0 before he hits the tree, and vertically his momentum is 0 after he hits the tree. He doesn't levitate or sink down through the asphalt. So delta P is P final. Remember, all quantities that are final get primes minus P initial. And that then is going to be equal to the force exerted by the belt times the time that that force is exerted. The final momentum is 0 because that is the mass times the final velocity minus, again, the initial is mv, and that's equal to the force exerted by the belt times the time. And this quantity is 0 because the final velocity is 0. So solving for the force exerted by the belt, the force exerted by the belt on the passenger. Notice we pick up a negative sign. That means that it's directed opposite to the velocity. We know that to change the velocity of an object, you have to exert, if you want to bring that velocity to 0, which is what the case is here, we have to exert a force in the opposite direction. And so we expect there to be a negative sign between the velocity and the force, and we assumed positive for the initial velocity as well. So this is going to be equal to a minus mv divided by delta t. And all of those quantities are over here, and I'm running out of room, so I'm not going to rewrite them. Imagine just moving mass in here and moving the velocity in here and moving your delta t in here. And when you plug all of those things in, let's see what you get here. So you're going to have 70 kilograms times the initial velocity, and then divided by the time that that force is being exerted, you're going to see a force of 2,700 newtons. And again, directed opposite to the velocity. It's a pretty large force being exerted by the seatbelt on the driver to bring him from an initial velocity of 10 meters per second directed in the positive direction to a velocity of 0. So that wraps up 8.8. Now 818 reads, a 0.40 kilogram hammer is moving horizontally at 7.00 meters per second when it strikes a nail and comes to rest after driving the nail 1.00 centimeters into a board. A, calculate the duration of the impact, and B, what was the average force exerted on the nail? Okay, so let's write down some of these specifics from the word problem. So the mass of the hammer is 0.450 kilograms, and we are told that it has a initial velocity, as before it strikes the nail, so no prime on that velocity, of 7.00 meters per second. And we are also told that that hammer is requiring a distance of, and I'll just call this x, 0.0100 meters to be brought from a velocity of 7 meters per second to a velocity of 0. So v prime is 0. In other words, the hammer comes to rest after it has been in contact with the nail for a distance of 0.0100 meters. So there we go with some of the information. Now we need to know what is the duration of the impact. Duration is indicative of time. So in A, we want to know what is delta t. Delta t equals question mark. And then in part B, we want to know what is the average force exerted on the nail. So the force exerted on the nail by the hammer. On the nail by the hammer equals question mark. So this is on nail by hammer. All right, so there's the two quantities we're out to find. So A, we want to find how long it took for the hammer to be brought from a speed of 7 meters per second to rest. So we start off with Newton's second law. The change in momentum of the hammer is going to be equal to the net force being exerted on the hammer times the change in time. And remember that the net force is being exerted by the nail, and so we can write the momentum then as the mass of the hammer times the final velocity of the hammer minus the mass of the hammer times the initial velocity of the hammer, and that's going to be equal to the net force times the time over which that net force has been exerted. Notice here that the final velocity is 0, so this cancels out. We know the mass of the hammer, we know the initial velocity. We don't know the net force being exerted on the hammer, and it's being exerted by the nail on the hammer. And so that's a quantity that we actually want to find in part B, and then delta t, which is what we're looking for in A. So we actually have two unknowns here. So we're going to need to go off and find another relationship that we have looked at in previous lectures and previous chapters to see how can we find the amount of time that that it took to travel this distance of 0.0100 meters. So let's look at this quantity called work that we looked at some time ago. So work and I'll just use the symbol W. We don't need a subscript. Work is equal to force times time. Or sorry, times dotted into displacement. Sorry, dotted into displacement. Okay. And from the work energy theorem, we know that work is also equal to the change in the kinetic energy of the hammer. So I can say that the work done on the hammer is equal to the force exerted on the hammer times the dotted into the displacement of the hammer. And I can also write that the work done, the total work done on the hammer is equal to the change in kinetic energy of the hammer. The only entity doing work is the nail. So I'm going to actually take these two and equate them. So I'm going to say that the change in the kinetic energy is equal to the force being exerted dotted into the displacement. And so if I write out what change in kinetic energy is, that's 1/2 mv final squared minus 1/2 mv initial squared. And that's going to be equal to the force being exerted by the nail on the hammer is oppositely directed to the displacement of the hammer. So I'm going to pick up a negative sign from this dot product right here. So this is going to be negative, and that's going to be the force exerted on the hammer by the nail. And this is times the displacement, which I know that displacement, and I've already given it a symbol of x. Now the final velocity is 0. Notice that here now I only have this one force that I don't know, and this is the force being exerted on the hammer by the nail. And of course that's exactly the same as this net force, which is changing the momentum of the hammer. So that is the force being exerted on the hammer by the nail times the time. So here I now have two equations with two unknowns, both of which I want. So let's go ahead and solve this lower equation for the force, and then once we have the force, we can come back up here and solve for the time. So in this particular problem, I'm first of all finding B, and then I'm going to solve for A. So I'm going to actually put A and B here because we're solving them simultaneously. Notice that one concept we started off with was the concept we learned here in this chapter, in chapter 8, but then we realized we had two unknowns, so we went back and looked at previous concepts we've learned, and work was the one that I wrote down because we were able to write down an equation that has the same two unknowns that were, or the same one unknown we didn't know from the previous equation. So solving this, we can see here that the force being exerted on the hammer by the nail is equal to, notice that these negative signs are going to cancel, and this is just going to be 1/2 m the initial velocity squared divided by how far that nail was driven. All those quantities are defined over here, so let's just go ahead and plug them in. So this is going to be 1/2 times the mass of 0.45 times the initial velocity 7, and we got to square that. And then we're going to divide that by the distance the nail was driven in. And this value is 1102.5. And the units are going to be joules per meter, or newtons, which are the units that we want for force. And so this answers part B. And notice that I actually have it written here on the nail by the hammer. That's specifically what we asked for, but that magnitude's the same as on the hammer by the nail. They're in Newton's third law pair. So this is the answer. It looks like this is a 3-fig problem, so we're going to write this then, or express the final answer then, as 3 figs 1.10 times 10 to the third newtons. Okay, so there's the answer for part B. Coming up now we can find part A, which is our delta T. So from this then, delta T is equal to a minus mv divided by the force exerted on the hammer by the nail. Notice time can't be negative. This negative sign comes from the fact that the hammer is experiencing a force oppositely directed to the hammer's velocity. That's the only thing that negative sign is telling us. And so we would plug in a negative sign also for this force being exerted on the hammer by the nail, and the negative signs will cancel. So this is the force we're going to plug in. And so now we take the mass of the hammer, 0.45, and we multiply by its initial velocity 7, and then divide by the 1102.5, which is the force, and we find that this time it takes to bring the hammer to rest is a 2.86 milliseconds. So that's milli, that's times 10 to the minus 3. So a very, very small amount of time here. So these two are the answers for A and B. All right, so that is 818. And lastly now, let's go ahead and do 836. 836, we actually deal with a collision in this particular problem. So 836 reads, a 30,000 kilogram freight car is coasting at 0.850 meters per second with negligible friction under a hopper that dumps 110,000 kilograms of scrap metal into it. What is the final velocity of the loaded freight car, and how much kinetic energy is lost? So in this space right here on the board, we're going to go ahead and try and finish off this problem. So first of all, we are told that the mass of the freight car is going to be equal to, and I got to use a subscript because we're going to have two different masses here, 30,000 kilograms, and we're told that the mass of the scrap metal that's going to be dumped into the freight car is 110,000 kilograms. We're told that the initial velocity of the car along the horizontal is 0.850 meters per second, and the initial velocity of the scrap horizontally is 0. It does have a vertical velocity. It does not have a horizontal velocity. It's being vertically dropped. So we're only dealing with the horizontal velocities here, no vertical velocities. All right, so what is the final velocity of the loaded freight car? Okay, so there are no external forces horizontally acting. We are told that the friction can be neglected, and actually friction is irrelevant as long as we consider the nanosecond before the scrap metal hits the bottom of the car, of this freight car, and the nanosecond after it's hit the bottom of this freight car. Those two momentums will be exactly the same. So in part A then, we can say that the initial momentum of the system is going to be equal to the final momentum of the system, and the system being the car and the scrap metal, and of course this is applied horizontally. Okay, in other words, we're only dealing with the horizontal dimension here. So the momentum of the system before, so this is going to be the mass of the car times the initial velocity of the car plus the mass of the scrap times the initial velocity of the scrap, and that's going to be equal to the mass of the car plus the mass of the scrap, because they're now moving off at one velocity, times their final velocity. So the final velocity then, and in the mass of the scrap, or sorry, the velocity of the scrap is 0, so that goes away. So then the final velocity can be written as the mass of the car times the velocity of the car before its collision with the scrap is equal to the mass of the car plus the mass of the scrap. Notice I'm calling it a collision. It is still a collision. Mass of scrap is colliding with mass of car, so it's still considered a collision. So I have these things defined up here. Let's go ahead and plug them in. So the mass of the car is our 30,000. And we're going to divide that by the sum of the two, and then multiply that by the initial velocity. And so we get a final velocity of 0.182. So final velocity equals 0.182 meters per second. Notice that the sign is the same. I assumed a positive direction. I get a positive direction. We know that. That's intuitive to us. And so I'm going to express this, since it's a two-fig problem, as 0.18 meters per second. In part B, we want to know how much kinetic energy was actually lost. And so we want to compare the initial and final kinetic energies. So kinetic energy lost is going to be equal to the initial kinetic energy minus the final kinetic energy. So that's the amount of kinetic energy was lost. Notice no prime for initial and a prime for final. So this is how much was lost. So before the collision, we have 1/2 mvc squared. Notice that all of the initial kinetic energy is in the car. And now we're subtracting the final kinetic energy, which is going to be 1/2, and this is now the sum of the mass of the car and the mass of the scrap times their final velocities squared. All right, so let's go ahead and plug that in. So the kinetic energy lost, again, and I'm going to just write it out so that we can see it. I ran out of space a little bit here. We have all these quantities already defined. We'll just plug them in our calculator. Okay, so how much kinetic energy is lost? So plugging this in, we have 1/2 times the mass of the car times the initial velocity of the car squared. So this number is, I'm doing them separately because I'm using kind of an older calculator that I just see one line at a time. So that's the initial kinetic energy that was all in the car to begin with. And now what do we have after the collision with the coal? Plugging in those quantities we already have here, this is going to be minus 2318.68. And so the amount that's lost then is significant, and it is 8,500 joules, going ahead and just rounding to 2 figs, which this problem is a 2 fig problem. So there we go. We see the amount of kinetic energy that is lost, part B, is much larger than 50%, and that is due to the fact that it has reduced its speed by quite a bit, picked up a lot of mass along the way, and that's due to the fact that the momentum hasn't changed horizontally along the system. So there we go. This gives us an idea of how to solve 3 different types of problems. And we will look at elastic collisions in the next video. They're a little bit more complicated to solve, and we're also going to derive an equation that's going to be very useful for us in solving elastic collisions. Note, this is an example of an inelastic collision. Anytime you have 2 objects that stick together, that is definitely, without a doubt, an inelastic collision. If they don't stick together, you don't know whether it's elastic or not until you compare the kinetic energy before and after the collision. So we'll talk more about that next time.